Alright, so today we're going to be talking about linear motion. Linear motion basically means the motion of anything in a straight line. So linear motion is when you have motion in a straight line, acting in a straight line. Alright, it could be this way, it could be that way. Doesn't matter the direction as long as it is going in a straight line. Alright, so when you have motion in a straight line, when something is moving in a straight line, you have four important components of it. The first component is called displacement. This is also known as the distance that it is covering. So let's say if we're looking at a ground, all right? So if we have a ground, let's move this over here. If we have a ground and there is, let's say there is a ball on this ground, all right? This ball, is going to be moving from one point to the other. So let's call this the first distance. Let's call it x1, and this is x2. All right. So if this ball is moving in this direction, all right. So there's motion in this direction. This ball is going to reach, let's say, over here, and it's going to have a specific displacement. So the displacement is basically the distance that it will be covering in a specific direction. All right. So this is going to be our displacement, which is delta x, which is also x2 minus x1. So whatever the position x2 minus the position x1. This is also known as displacement. The difference between displacement and distance is displacement is a vector. All right. So we'll call this displacement a vector. It's also the units of this in meters. The SI units of it is in meters. And distance is a scalar quantity. So if you recall, the difference between scalar and vector, all right? So scalar only has a magnitude, while a vector has a magnitude plus a direction. That is the most important thing you need to know here. So when you have a displacement, you basically have a specific direction it is moving in, going to the right, going to the left, going up, going down. So there's a specific direction. Distance is just the value of it. So it's 5 meters, it's 10 meters, it's 20 meters. So the vector, you would say 20 meters to the right, 20 meters up, 20 meters down. So the displacement in this case would be 20 meters to the right, for example, if this was 20 meters, or delta x to the right. Right, that is what displacement is. Scalar is just this actual distance, the value of the distance here. It's not the direction the ball is moving to, but just saying the distance from this point to this point. All right, so this is the major concept that you need to know, that there's a difference between a scalar value and a vector value. The displacement is a vector value, while the distance is a scalar value. The units of distance is m, and usually displacement is given as the letter s. All right, so it's s, and it is the letter in meters is the unit. Now let's look at the next component. The next component is velocity. Again, velocity is very similar to speed. All right, the difference being velocity is the vector, so it has a specific direction we're talking about. And then we have the speed, which is just a scalar value, which is just the value of it. So a movement, a speed. The direction doesn't matter in the scalar value. For a speed, it has no specific direction. It's just the speed. It's just a magnitude. Velocity will have a specific direction. So in this case, let's say there is a specific velocity that this ball is moving. All right, from here. All right, and then it's going to have a specific velocity when it reaches this point as well. Okay. So it's going to have a velocity v1 over here, and let's call this velocity v2, which we will talk about even more in a little bit. Now, velocity is in meters per second. That is the units. It is basically the amount of displacement that it is covering over a specific amount of time, which we will look at in a little bit as well. And it is usually given as the value v, or the variable v. Moving on. After that, we have acceleration. All right. Number 3, the third variable is acceleration. Acceleration. And this is a vector quantity all the time. Usually there is no scalar value for acceleration. It is just a vector. And this is going to be in meters per second squared. and this is usually given the letter A for it. Last but not least, the most important thing, as we call our fourth dimension, which is time. Right? So we have time. Time is a scalar quantity. Time doesn't have any specific direction. Time is always increasing, obviously, but it doesn't. We have no direction for it. It's a scalar quantity. All right, and it is usually given in seconds, and t is usually the letter that will denote time. So if we look at this ball example, this is going to have a specific acceleration in one direction. In this case, it's going to have an acceleration in this direction. All right, and time is going to be the time it takes for this to reach from this area to this area. So here we're going to have t1, and here we're going to have time 2. All right, so this is the initial time, and this is the final time, which we'll talk about now. So usually I'm writing here t1 and t2. This is basically meaning this is case 1, like this is the initial case, and this is case 2, which is our final case. All right, so this is how we will always be identifying things. We will always be identifying our displacement, our velocity, and our time with an initial value and a final value, because it will always be dependent on where it was and where it is going to reach. And acceleration is just always going to be there, present. All right, it might have an initial acceleration of 0 or a final acceleration of at a specific point as well, but most of the time, if there is already motion from the beginning, that means it has an initial acceleration that is being a part of causing that motion. So acceleration will always be causing the motion. This will not be moving if there isn't an initial acceleration to it, and it will never reach the second point. Let's talk a little bit more about this in detail when it comes to initial and final values. All right. So, as I was saying earlier, we have initial and we have final. So usually the way they would write this is, instead of writing x1 and x2, v1 and v2, they will be writing, so this is our final phase and this is our initial phase, they will be writing this. They will be writing x0 and xf, meaning x initial and x final. All right, so when you have the subscript of O, this means it is initial. All right, so whatever factor here is, and if we have f, this is final. All right, this isn't A, this is just any variable. So whatever variable you have here, if you have O, it is initial, and if it is F, it is its final velocity, displacement, or time. Same thing with time. Usually they would call this here time 0, and this is time final. And the time it takes, the total time, will be the change of time, which is equal to Tf minus T0. Same thing with x. This is going to be x final minus x initial. Okay? And you can say the same thing about the voltage. It's voltage, sorry, I'm talking about velocity here. We're going to have the same thing with the velocity. This is the velocity final, and this is the velocity initial. So, how do we relate all of these variables now together? To start off with the simple case, let's talk about just the velocity or the speed even. If we're talking about speed, okay? Speed is going to be equal to the distance over time. Very simple, very straightforward equation. Yani, the amount of distance this will cover, all right, over time. If we take an example, so let's say we have a ground here. Okay, we know that the distance from here to here, let's say from this point to this point, is 10 meters. Okay, and we have a block, whatever, it's being pushed from here to here. All right, so it's moving with a specific speed, not a velocity, so it doesn't have a direction. We're talking about scalar quantities here. This is scalar. This is also scalar. And this is scalar. So our values are all scalar, okay? So it's going to have a specific speed from it reaching from here to here. that we need to find. So we'll call this speed, I'll call it speed. We have a specific speed, and I'm telling you the time it takes for it to go from here up to here. It takes 10 seconds, or let's say 20 seconds. Okay, 20 seconds. So since it's taking 20 seconds, the simplest way to find speed will be, the speed is going to be equal to the total distance, which is 10 meters, divided by the total time, which is 20 seconds. So if we simplify this, we are going to get 1/2, or half a meter per second. So this is the speed that this was traveling at. Again, we don't care about the direction. We just care about the fact that the magnitude exists. We know that it is going in a specific direction, but we're only looking at the value of the magnitude. This is when we are using distance. We are using speed instead of a displacement and velocity. It is just a simple equation where the speed is equal to the distance over time. The same question if we want to talk about velocity now. So if we want to talk about velocity, velocity is a vector value. So it will have a speed and a specific direction. So this is going to be equal to the displacement. It's no longer the distance, it's the displacement divided by time. The reason it is now displacement and not distance is because time, we know, is always a scalar value. But we cannot have two scalar values give you a vector. We need to have at least one vector value so that you can get a final answer as a vector. All right? So in this case, if we look at the same case again, now we are going to say that this is the block over here, the initial place of the block, and this is the final location of this block. Okay? And it was moving in this direction. So this is the most important point now. We are saying we are determining the direction of motion, where it is moving. Okay, so the motion is going into this way. Here we're going to have an initial distance. Let's call this a distance, or an initial displacement, I should say, x0, which is equal to, let's say, 5 meters. And let us call this displacement over here the final displacement of 20 meters. Okay? Now we know that there is going to be a velocity acting on this, going into this direction. All right? The most important thing here is this is going to be V0, and this is going to be V final, which we are going to try to find. All right? So, and I tell you time is a scalar value, so I can tell you the time it takes, or I could also mention it this way. We say that time 0, it starts at 0. Okay, we can make it simple. It just starts at 0 seconds, and the time it reaches is 10 seconds. After 10 seconds, it reaches this point. We are still missing one variable. Since we are dealing now with vectors, we have to know what is the initial velocity and the final velocity as well. We need to know if it was starting with a movement or not. So I will say it is starting at rest. What does this phrase mean? Starting at rest. So when we say rest, this basically means that our initial velocity is going to be equal to 0 meters per second. As in, this object was not moving or was not accelerating, all right? So there is no initial velocity for it. At this point, there was no acceleration at all. Hence, there is no initial velocity. Okay? So it started from a point where the velocity was equal to 0. So now we can find our final velocity. And how are we going to do that? So the equation basically will be V final minus V0 is equal to the displacement initially, or the final displacement, I mean, minus the initial displacement divided by the final time minus the initial time. Okay? If you notice here, we can cancel out a lot of these things. Why? Because they're equal to 0. We can say that the velocity final minus 0, because we already know that this is starting at rest, is equal to the displacement xf is 20, the final displacement is 20 meters, minus the initial displacement was 5 meters, all right? Over the final time was 10 seconds, minus the initial time, we said it starts at time 0. So it started moving at time equal 0. Now we see we can solve this easily and say Vf is going to be equal to 20 minus 5 is simply 15 meters over 10 minus 0, which is 10 seconds. This is going to give us that the velocity is 1.5 meters per second. Okay, this basically is just the scalar value of it. Okay, what would usually determine the direction is if this was positive. Since this is a positive value, we know it is going in the positive direction. So to make sure how we know our positives from negatives, we have to assume our positive directions. So here, initially, I said the motion is going into that way. So we have assumed that this is our positive direction for motion. Okay? Since I have assumed that, this positive means that this velocity is going to the right. If I have assumed that our direction is going to the left, a lot of changes will occur, and we will see an example in a bit about that. All right? So this is simply how you would solve a basic velocity question for velocity and displacement and time. Now let's try to relate acceleration to all of this as well. The acceleration, or I should say the average acceleration average, is going to be equal to the change in velocity, which is v final minus v initial, divided by the time, or the change in time, which is t final minus t initial. Most of the time, t initial is most of the time assumed to be equal to 0 unless mentioned. So this is always most of the time assumed as 0. So we're just going to keep assuming that the initial time is equal to 0 unless it is specifically mentioned. So this equation can be rewritten in this following way. It can be written as v minus u over t, where u is the initial velocity. This is just another way of writing the initial velocity. It is commonly written as u, and v is usually as the final velocity. Okay, it is just the way they are to, يعني it's just a notation, it's just the way to write it. ما في فرق ابدا اذا كتبناه بهالطريقه او هالطريقه, as long as you understand what you are doing. This is just a notation. So now we have an equation for acceleration. So acceleration, or the average acceleration, all right, is going to be equal to the final velocity, or the change in velocity, I should say, which is final minus initial, over the time. Okay? Usually, in a question, acceleration, if it is not changing, if acceleration is not changing, in other words, we say that acceleration is a constant, so it's given a specific value. The average acceleration is going to be equal to just the instantaneous or the normal acceleration. All right? So most of the time when we are dealing with acceleration, acceleration is constant. We're not having different values for acceleration. It is going to be given as, for example, 2 meters per second squared, and that's the acceleration throughout. And we will be looking at that. So now, going back to the same question over here, we have determined our final velocity early on. So we have determined our final velocity from this previous question. Let me just bring it back down over here. So from this question, we have determined, we can rewrite this now as this being u, meaning it is our initial velocity, and this just being v, which is our final velocity. All right? We know that u is equal to 0 because it is starting at rest. And we have already found v to be equal to 1.5 meters per second to the right, or plus 1.5 meters per second. Okay? We have assumed, remember, that this is the direction of motion. So we can also know that acceleration is most probably going to be in the same direction, because how else would it move? but this is where we have assumed our positive motion is. We have assumed this direction. So if we want to now find our acceleration, acceleration again was equal to v minus u divided by the time t. In other words, this is going to be equal to, what is our final velocity? It is 1.5 meters per second minus 0, because our initial velocity in this case is 0, divided by the time it totally takes. So initial time is 0, so tf is the only time there is, so which is 10 seconds. Because it is tf technically minus t0, but we will always assume t0 is 0 unless in a certain situation it is otherwise. All right? So it is over 10 seconds. So now we can find out that our acceleration is equal to 1.5 over 10, which is equal to 0.15 meters per second squared. If you notice, we have meters per second divided by second, so it is over seconds squared. And this is how you would find the acceleration for any problem, for any simple problem. Okay, so you'll always have to look at what your initial case is, initial resting position, or if there's an initial velocity. It depends on the question, whatever it gives. Here we have already just assumed that this is our initial velocity is 0. Then we can look at our final velocity, or get it if we are given our displacement values, and that's pretty much it. And then if we're given time, we can find basically the acceleration as well. So acceleration, since it is as well a positive value, the acceleration is going into this direction, and it is a constant acceleration. All right, that's why. So constant acceleration basically meaning the initial and final acceleration is the same. It is not changing. All right, and this would be the case for this would be like mostly the case in most of the situations that we are going to be dealing with. So let's just do a quick recap now. We have found out that over here, the first thing we said is velocity is displacement, or the change of displacement over time. So we know that velocity v delta v, I'm going to mention it as delta v, is equal to delta s, where s is the displacement, over delta t. Okay, I'll tell you why I'm writing it in this way. Delta v basically means the change in velocity. So it is v minus u. All right, so it's final minus initial. The same thing for displacement. Delta s is equal to x final minus x initial. All right, the same thing, or usually we write it in terms of s. So I'm going to just write it as s final minus s initial. And delta t is equal to t final minus t initial. Since we are assuming that t0 is always, assume that t0 is equal to 0 in most cases, we can simply say that delta t is equal to the time taken, or the final time. So now if we want to simplify this equation, we're going to have v minus u is equal to SF, or delta S, okay? Or simply we can do it in this way. We can mention this as XF minus X0 is equal to S. All right, this is a better way, so that we can always use just S as our displacement over the delta t we said is always going to be equal to t final, which we will simply just call t over time. So if you notice here, now we have a general equation that relates velocity and distance and time. Let's do the same thing now for acceleration. So we know that average acceleration is also equal to the acceleration if acceleration is constant. So average acceleration is going to be equal to the change of velocity over the change of time. All right, this is what this means. We have already mentioned what the change of velocity and change of time are. Let's look at average acceleration. So we said that average acceleration is going to be equal to acceleration when a is a constant. And most of the cases, our acceleration will be a constant. Okay? So we can rewrite this equation now as a is equal to delta v is just v minus u over delta t is just t final, which is just the time t. Okay? These are all the basic equations we have. These are the basic equations, and from these two basic equations, this is the first one. Okay? This is our first basic equation we have. We can derive all, and this is the second one, and we can derive all other equations from these two main equations. Let us see how. So first, if we just take these two equations again, let's look at the very first equation. This equation over here. Okay? If we look at this equation, we will notice that we can just take this u to the other side. All right? So the one way of doing this, so we can notice that we can get an equation for final velocity. It is going to be equal to s over t. Okay, s divided by t plus u. All right, all I did was I took the u from this side to the other side. So this, all I did was move u. Okay, and now we have an equation for velocity that is based on initial velocity, displacement, and time. Same thing again. We can rearrange it in another way so that we can arrange it so we can find s by itself. So if we want s by itself, this can be rearranged. We're just going to multiply t. So what we're doing here is we are multiplying t on both sides of the equation. When you multiply t on both sides, the t on the right side will cancel, and the left side will remain with v minus u times t. Okay? So this is another form of the equation that you can see. You can also rename this v minus u as delta v, for example. Okay? It's the same thing, because remember, v minus u is delta v. But this is just another form. Another form as well, okay, we can have, which is not very commonly used, but another form that you can also have is you can have the whole equation to find the time. If you are given all of these, you can try to find time. So this is going to be equal to, how are we going to find time? We are just going to multiply everything by time and then divide by v minus u. So we're going to multiply by time, then divide by v minus u. Okay? And you will see how that will look like in a little bit. So we will divide by v minus u, both sides of the equation. So you're going to first multiply by time. It will cancel the time. We'll get this. When we multiply by time, we get this equation, right? The s equal v minus u times t. So here, if we just divide by v minus u on both sides, it will cancel, and we will remain with this s over v minus u. V minus u. So from this one, we have already found like 3 different ways that we can rearrange this equation so that we can find 3 different values. We can arrange it one more way as well to find u, all right, if we want to, which is possible. I'm not going to do that, but because it's simple, all you're going to do is in this case, so if we want to find u, all right, let's just do it very quickly. We're just going to move the s over t to the other side. It's going to be v minus s over t. Okay, that's it. But this is very easy, like it's a very straightforward one. All of them are very straightforward. You just have to know how to do your basic algebra, your basic transposing of a formula, so that you know how to get it in terms of anything. So now we have looked at the first equation. Let's look at the second equation, which is the acceleration equation. Again, you can do the same thing over here with the acceleration equation. You can find different ways of relating it with each other. So the first thing we can do, for example, is first thing we can do is multiply by t. So multiply by t. And you will notice that we'll have at and multiply by t, and then we'll say we will add u, and I will show you why. So first, if we multiply by t, we are going to get a t is equal to v minus u. All right, so v minus u. Again, so this is just a times t. Why? Because the t will cancel on the right side, and the left side you will have a t. And then we can add u. So from this step, we're going to just add u, or move u, I should say. So move u to the other side. And we will have this equation over here. V is equal to at plus u. So a times t plus u. All right, so now u is positive because we moved it to the other side. All right, so v is equal to at plus u. This is one of the most basic equations used for velocity when you have acceleration instead of displacement. This is how you will find velocity. Moving on to another way. So let's look at another way we can rearrange this equation. Okay, we can simply do this over here. Okay, and we can simply just move around the v and the u. So let's try to find this in terms of t, for example. Okay, so if we want to find it in terms of t, all we're gonna do is multiply by time at first. Okay, and then we're gonna divide by acceleration on both sides. That's what we are gonna do. So if you notice in the first equation, when we multiplied by time, we got at is equal to v minus u. So once we divide by acceleration on both sides, we're gonna cancel acceleration here, and this is going to be equal to v minus u over the acceleration. Okay, over acceleration. Of course, you can do the same exact thing again to find u by itself, and you can find the velocity as well. We already have found the velocity as well. And if you are using these together, you can also find out equations that you should know by now that involve both velocity and speed without time, or even an equation that involves acceleration without velocity and only displacement. So some of these equations look like this. So velocity squared is equal to u squared plus 2 times as, which is acceleration times distance. This is an equation you can get without having no time. So this has no time. All right. Another equation can be written as S is equal to ut, u times time, plus half at squared. Okay, this is another equation that you can rearrange and write by finding it without no final velocity. All right, final velocity. This is another formula you can use if you're not given that. So if you notice here that we don't necessarily have to just use these. So in this case here, we have no displacement. So if I just bring down this equation again, which is a is equal to v minus. So if we take it into this form, because this is the more general form, if we look at this, okay, in this case we have no displacement. S, right? So here we have no displacement S. This is no velocity, the v, and the first one was no time, which is t. And if we look at our last equation, or the very first one I should say, this equation is the first one that we have derived, that velocity is equal to s over t plus u, okay? Or another way of looking at it is s is equal to v minus u over t. This is a more generic one, okay? This is an equation with no acceleration. No acceleration. This doesn't mean acceleration does not exist. No, acceleration will exist, all right? But This means that you can find a formula in any, like here we can never say time doesn't exist. Time always exists. But the idea here is if you have 4 of these, okay, I mean if you have at least 3 of the variables, you can find the 4th one without having to find all the variables. But if you notice, initial velocity is always a must. If you do not know what the initial velocity of, so if you notice here, we have initial velocity, initial velocity, initial velocity, and initial velocity. You always need to know what your initial velocity is to be able to solve at a specific time, all right? There's one more thing, sometimes you will see written around. You will see it as S is equal to V average, all right, times time. In this case, and I don't want there to be too much confusion here, in this case, this average velocity, V average, let's highlight it as well. So V average, bad color choice, V average is different than V minus U. What does V average represent? So V average basically represents, it's equal to the final velocity plus the initial velocity divided by 2. This case will be only used when you do not have a consistent velocity. So your velocity is not consistent. You can use this instead to solve instead of V minus U over here. So you could just find your average velocity so that you can find out your average displacement depending on the time you have. All right. So this will be, again, for this not to be confused with the displacement equation or the original delta V. This is not delta V. This is V average. All right. This is V average. Okay. This is how you will be using this equation. And that's pretty much for it for all the major concepts when it comes to linear. But let's go over just some basic concepts that you guys should already know. If we are talking about a body that is falling freely, all right? So what does that mean? If we have a body that is falling downwards, okay? So let's call this like a ball or something that is falling downwards. If this ball is falling downwards, we know that it's going to have a specific weight that is pulling it down. So it has a specific mass m, and we know it's going to have a specific weight, and this weight is equal to the mass times the gravity constant, which is usually 9.81 meters per second squared. This is old knowledge. All of you should know this by now. So F is equal to MA is basically, this is another form of it. So what is F equal to MA? It's the force is equal to the mass times acceleration. Most of you should know this by now. So this is the force, which is in newtons, the mass, which is in kilograms, and the acceleration, which is in meters per second squared. Why is this important? Because now we are dealing with this acceleration, or we will be using this acceleration using all the linear equations that we have learned before here, so that we can determine that what the F value is based on a specific mass of an object. So if an object is moving at a specific mass, with a specific mass, I should say, at a specific acceleration, we can find out how much force is being exerted. So when we're talking about a free falling body, the weight is our force, and the gravity is going to be our acceleration. So we use G as our acceleration. In other words, we can also say that this is W is equal to mass times acceleration. The difference here is we know in this case that acceleration is equal to 9.81 meters per second squared. All right. And W is our force. That's basically it when it comes to a free falling body. Free falling body meaning that this is a body without any other forces up or down acting on it. It is just falling from the sky towards Earth. Okay. So free falling body. This is just a general concept that you guys should already know, but this is how it will be used. One last thing is direction for this exact example. So usually it is assumed, if we're assuming our positive direction to be downwards, if this is our positive direction, remember that acceleration is a vector, so gravity is a vector. In this case, G is also positive. So our weight is going to be a positive value. If we are assuming it in the opposite direction, if we are assuming our positive direction to be upwards, then it's based on your assumption on how you analyze things, okay? It doesn't matter whether you're choosing up or down. Logically, if it's a free falling body, we'd logically use down as our positive because there's nothing else. It's all going downwards, so we can keep everything positive. But if we have our positive direction be upwards, our G will be negative, okay? Because remember that gravity is always acting in the bottom direction. So gravity, G is always going downwards in both cases, okay? That is why. So it depends on the direction you assume, and this is a very important thing when it comes to solving all of these questions in general. This should be the most important focus on knowing how to assume your directions.